Greetings of the day to all of you. Welcome to this lecture on Introduction to Multi-Level Converters. As far as my knowledge is concerned, I think you have already covered multi-level converters in your course on PWM techniques, and multi-level converters have been covered in greater detail in that course. However, in this course, that is Modern Power Electronics, you are supposed to cover only the space vector modulation for multi-level converters in greater depths. But before we begin to understand space vector modulation in the context of multi-level converters, we also need to recap these converters a bit and to introduce them to you again from the context of switching states, and a brief idea of converter performance will also be specified in this lecture. So before we begin with an introduction to multi-level converters, I would like you to remind yourselves of the standard two-level VSI, that is voltage source inverter, also known as a two-level converter, which has two switches on each leg which are complementary in action. And if you have a three-phase two-level VSI, then you will have three such legs. The middle point is of course connected to the load, and if you split the DC input DC voltage to create a pole, a fictitious pole, let's call it O, then if the input voltage is VDC, the capacitor voltages will be VDC by 2, VDC by 2. And we also know that if the switch S1 is on, then the pole voltage VAO, that is the potential of this point with respect to this point, will be plus VDC by 2. Or else if S4 is on, which is a complementary switch of S1, then VAO is simply minus VDC by 2. So the pole voltage in a two-level converter is it can assume two values, that is plus VDC by 2 and minus VDC by 2, and therefore it is called as a two-level converter. What we generally tend to do is that you may operate this converter in a square wave mode, where for half of the time period you will switch S1 on, and then for the remaining half of the period you will switch S4 on. So you will have plus VDC by 2 for 50% of the cycle and minus VDC by 2 for the other half. However, in this case, the output voltage is a square wave and it is riddled with lower order harmonics, which gives us poor harmonic performance. Especially there are third harmonics, fifth harmonics, seventh harmonics, and so on. However, an interesting way is to go for a PWM technique, for instance sine PWM, or in case it's a three-phase inverter, then even space vector PWM, where you tend to rapidly switch S1 and S4 on in such a way that their instantaneous averages follow a sinusoidal pattern. So in the positive half cycle it remains more positive, the averages follow something like this, and in the negative half cycle it remains more negative, something like this, and the instantaneous averages follow something like this. So this is how we approximate using by simply sampling the input DC voltage at the output in a sinusoidal manner, that is frequency modulation. If you talk in terms of communication systems, which you may have studied somewhere in your BTech, you're basically sampling this VDC at this point A with respect to the point O, and whether it's plus VDC by 2 or minus VDC by 2, that is being sampled at the output. This is done in such a way that the sampling gives you a sinusoidal representation, or you can say that the instantaneous averages of this output voltage waveform is a sine wave. So you have a fundamental component at your required frequency, say 50 Hertz. Now, the problem with the two-level converter, and the reason why we go into multi-level converters, is that in order to get the best possible approximation of a sine wave, you may have to go for very high switching frequencies. The higher your switching frequencies, the higher are your harmonics, the higher order, the more higher order harmonics will be present in your output voltage waveform. Or in other words, you can say that it will be very easy to isolate this fundamental component from the rest of the higher order harmonics, especially if the switching frequency is very high. Or in other words, you can say that when the switching frequency is very high, you are better approximating a sine wave with something like a frequency modulation technique, like a sine PWM technique. The problem is that if you talk about high power applications, then very high switching frequencies may not be desirable, because you know that switching frequency directly impacts the switching power loss. We have in fact calculated switching power losses in switches, and we know that they are directly proportional to the frequency of switching. So if the frequency of switching is very high, which is of course desirable because I know that it gives me a better waveform quality, then at the same time the loss, switching power loss in the circuit is also very high. And when we talk about high power converters, multi-level converters are also known as high power converters because they are usually used in high power applications. So when we talk about high power applications, we know that we are dealing in power of the order of, say, megawatts, or hundreds and thousands of kilowatts. And there, even 1% of loss amounts to a very big a very big value. Even 1% of power loss may be as high as 1 megawatt, and it's not always easy to find so much space to dissipate 1 megawatt of power. Therefore, in very high power applications, you do not want very high switching frequencies. You want low switching frequencies so that there are low power losses in high power converters. So someone came up with the idea of multi-level converters, where basically the two-level waveform, because even though you're modulating it very fast, you are still oscillating between two levels, that is plus VDC by 2 and minus VDC by 2. So somebody proposed, what if we create something like a staircase somehow, and our output voltage waveform is no longer sampled between two values but between multiple values. So the amplitude keeps changing. So it's like, say, VDC, then 2 VDC, then VDC again, then minus VDC, VDC 2 minus 2 VDC, something like this. So something like a staircase waveform. This we can directly get, which means that even without going into very high frequency modulation or very high frequency switching, we can better approximate the sine wave, especially if you have much higher number of levels, something like this. You know, if there are too many levels, then of course you are approximating it even better, something like this, right? So the higher the number of levels, it means that the higher is your approximation to a sine wave, and without even switching the devices. Of course, you will require a larger number of devices and a change topology, which we will discuss very soon. But without causing very high frequency switching, you are able to get a more sinusoidal waveform with low THD, with no presence of lower order harmonics. So these kind of converters, you tend to use them in high power applications where you can afford to use a large number of devices as a one-time investment, as an initial investment, but you are drastically improving upon your running costs because you are saving on a lot of power, because you're not switching your converters at very high switching frequencies and you're not causing any power losses. Of course, they're expensive to begin with, but in the long term they give you more power saving benefits. Without adversely affecting the waveform quality. So multi-level converters are of three major types. One is the Cascaded H Bridge, which is the most simplest in my opinion. The Cascaded H Bridge topology, which is basically a lot of two-level converters cascaded together to give you multiple levels. We will discuss this in detail. The second is the neutral point clamped converter. Neutral point clamped converter, very often called as the NPC, or it is also called as a diode clamped converter. Neutral point or diode clamped multi-level converter. And the third, which is not really used very frequently, is the flying capacitor type of multi-level converter. There are also modifications in all these topologies to give new topologies of multi-level converters, but I think these three are the basic fundamental types of multi-level converters. Even then, the flying capacitor type of multi-level converter is not used very frequently because it is associated with a large number of capacitors, and that makes these circuits very bulky in nature. And the very essence of using power electronics, at least in the present times, is miniaturizing circuits, making them very small, and removing component count in terms of capacitors, inductors, because it's okay to use a large number of devices, but not very okay to use a large number of capacitors or inductors because they occupy a lot of size and volume in the converter. So it makes miniaturizing the circuits very difficult if you're using a lot of capacitors. So flying capacitor circuit we are not going to discuss, but yes, we'll discuss cascaded H bridge and neutral point converter, which we will eventually also study with space vector modulation. So let's talk about the cascaded H bridge. Now, you have a single phase inverter. Of course, each switch, I'm drawing like a switch, but it has an anti-parallel diode, and you must know that. But because I have a space crunch, so I'm drawing just a switch. You have a simple H bridge and a DC voltage source, say VDC, that gives you some output between these 2 points, right? Let's call that output as V1. So one end of this cascaded H bridge is connected. Your aim is, say, DC to AC conversion. So this is your input DC, and at the output you want to produce three-phase AC. So it is connected to the phase A of your three-phase load. The second output is actually cascaded to another H bridge like this. So you will have another H bridge over here, and this H bridge will have another DC supply, say VDC, which will be isolated from this DC voltage source. So this is a different voltage source, electrically isolated from this voltage source, and this is also going to give us some output. Let's call it V2, and we basically want V1 plus V2. So we are cascading them or connecting them in series, and we want these two to add up onto the load. So this becomes my, say, the neutral point of the load. So this is phase A. Then this leg will repeat a cascaded H bridge with two outputs, two leads at the output. Connected in cascade, this goes to phase B, and then this goes to the neutral point. Similarly, two more cascaded H bridges. One goes to point C, the other cascaded to the other H bridge, and this is connected to the neutral point of the load. So this is my neutral bus. This is leg 1, this is leg 2, and this is leg 3. I'll also explain how we'll get an output, but for now let's see the phase voltage we'll consider only one leg. Of course, this is all modular then, which means that it's easy to modularize cascaded H bridge based multi-level converter because you can just keep on adding H bridges without making many changes in the topology. So it's modular. Just keep on adding the same unit again and again, and you're going to increase the number of levels. Anyways, so let's understand the operation of this converter. So you have the phase neutral, that is N, and you have the phase point VA. So the phase voltage VAN is simply V1 plus V2, right? Because these are simply getting added in series, because you have two H bridges connected in series, their outputs are connected in series. Now, if we talk about just V1, this particular output voltage can either be VDC, which means if this switch and this switch is conducting, so one switching state of the upper bridge is contributing to V1 becoming equal to VDC, only one switch, right? Or this can also, or only one switching state, or this V1 can also be equal to minus VDC if this switch and this switch is on, right? So it can also be minus VDC, and again only one switching state, that is this is on, this is on, that is one switching configuration, will contribute towards V1 becoming equal to minus VDC. Apart from that, V1 can also be 0, which is when these two switches are on. That means you're simply shorting the output. In that case, your V1 is 0. Or if the lower two switches both are on, so either the upper two switches are on or the lower two switches are on, in either cases, your output of your converter is 0. So there are two switching states, two possible switching configurations that can generate 0 V1. So this is just about V1. Similarly, V2 can be either VDC, it can be either 0 or it can be minus VDC. And if it is VDC, that is only one switching configuration is generating it. If it is minus VDC, again only one switching configuration is generating it. But for 0, these two might be on or these two might be on. So there are two possibilities that will result in 0 state. Now what about VAN? And we know that VAN is simply the addition of V1 and V2. Now these can add in multiple ways. VDC and VDC can add up to become 2 VDC, and the possible number of the number of switching configurations that will cause it is only 1 into 1, that is only one switching state for the whole leg. 2 cascaded H bridges will generate 2 VDC at the output. Or this VDC may add up with this 0, right? So I can have VDC plus 0, or I can have this 0 adding up to this VDC. So 0 plus VDC. In either case, the result is simply VDC. That means VAN can also be VDC, right? But how many switching states will produce that effect? So when VDC is adding to 0, 1 into 2, so 2 switching states can cause it. And when 0 is adding to VDC, 2 into 1, again 2 switching states are causing it. So 2 possibilities for this and 2 possibilities for this, a total of 4 switching states result in total phase voltage being equal to VDC. All right. The third thing is the third voltage level that we can get is 0 simply adding to 0, 0 plus 0, and this is a combination of 2 into 2, so 4 switching states will result in it. Or minus VDC adding to plus VDC, minus VDC adding to plus VDC. This is only 1 into 1, so only one switching state will give this combination. And or VDC adding to minus VDC, VDC plus minus VDC. Again only 1 into 1, that is only one switching state will result in this combination. And all these are giving an output of 0. So an output of 0 is produced through 6 switching configurations, 6 switching states, right, of one leg. Similarly, you can have an output of minus VDC, which will also be, if you see the combinations, it will also be produced through 4 switching states. And then you can have an output of minus 2 VDC, which will be produced through a combination of only one switching state. So what my point is that the phase voltage VAN, this over here V1 plus V2, it will have 5 levels: 2 VDC, VDC, 0, minus VDC, and minus 2 VDC. So something like this: 2 VDC, VDC, 0, minus VDC, minus 2 VDC, and then repeat. So it's again like a staircase. This is your zero line, this is VDC, this is 2 VDC, this is minus VDC, and this is minus 2 VDC, right? So this is the output of a 5 level. These are 5 levels, 1, 2, 3, 4, 5, right? This is the output of a 5 level cascaded H bridge converter, or you may call it as a CHP, a symmetrical CHP. By symmetrical, I mean that each individual H bridge has the same DC voltage source value. VDC, VDC, VDC. हर किसी H bridge में जो DC source है, that is equal to VDC. Each VDC is isolated from the other, but the value is same. So each H bridge is fed by the same value. It's a symmetrical H bridge, and it's a 5 level H bridge, which also brings us to the point that the number of levels, how do we decide the number of levels, and how do we decide the number of H bridges that we want? So if I have, say, I require n level of convert in a cascaded H bridge, I require n number of levels. Then if I have H number of H bridges, then n is equal to 2H plus 1. In this case, per phase, we had 2 H bridges. So 2 into 2 plus 1, that gave us 5 levels. Or you can also simply manipulate this and write it as n minus 1 by 2, which means depending upon the number of levels that you want, you will select the number of H bridges that you want per leg, right? This also tells you that no matter what number of H bridges you use, the output phase number of levels in a cascaded H bridge multi-level converter will always be an odd number, because 2H plus 1 will always be odd. You can also find out the number of devices that you need in a cascaded H bridge converter. So in fact, this is the highest amongst all multi-level converters. So if you have n number of levels, you know that n minus 1 by 2 is the number of H bridges that you want per leg. And if it's a 3-phase inverter, then you may need 3 such thrice the number of such H bridges, and each H bridge has 4 switches. So this gives you the total switch count, right? So this is 6 times n minus 1, which means to generate a 5 level 3-phase inverter, you will require 5 minus 1 is 4, 6 into 4 is 24. You will require 24 switches. Similarly, you can find for 7 level, 7 minus 1 is 6, 6 into 6 is 36. You will need 36 switches for generating 7 level, so on and so forth. Now the good point is that suppose this particular case that we discussed, this was a 5-level converter. Suppose you require an 11-level waveform. Of course, the higher the number of levels is, the better is approximation of your sine wave. So suppose you require an 11-level waveform, an 11-level CHP you want to design. Then obviously the number of H bridges that you would require will be 11 minus 1 by 2, that is 10 by 2, that is 5 H bridges per leg, which means that if each leg has VDC, VDC, VDC at the input, so on and so forth, the 11 levels will begin from 5 VDC to 4 VDC to 3 VDC, so on and so forth. So the highest output, AC output, will be 5 times VDC. But each device will be rated only at VDC, because each device will be placed within an H bridge, and the H bridge is rated, the devices in an H bridge are rated to the input DC link, and each input DC link will only be VDC. So you will see that the output voltage is much more as compared to the rating of the device. The rating of the device is 1/5 times the highest level in the output. This is another beneficial thing in high power converters, not just that your power losses are minimized through multi-level converters, but also in high power applications where it is likely that your converter might be operating at say 11 kV or say 33 kV. Then even if your AC voltage is 33 kV, each switch, if you are using very high number of levels, each switch may be rated at a much smaller value, say only 1000 around say 33 kV by 5 if it's an 11 level converter. If it is a 5 level converter, then it will be only halved. जो हमने पहले केस किया उसमें आपका 2 VDC पीक आ रहा था, बट ईच डिवाइस वाज रेटेड टू ओनली VDC, सो हाफ ऑफ द वोल्टेज. अगर आप 233 kV पे 5 लेवल का कन्वर्टर लगाओगे तो आपकी जो डिवाइस की रेटिंग्स होंगी वो 33/2 kV होंगी, और अगर आप 11 लेवल का कन्वर्टर लगाओगे तो वो 33/5 kV होंगी. Right? So the higher the number of levels, the smaller will be your device ratings, but of course the higher will be your device count. ठीक है, तो ज़्यादा से ज़्यादा devices लेकिन छोटी से छोटी ratings के devices. You should also know that when we go to purchase devices, generally it's cheaper to have a larger number of low power rating devices than a higher as compared to a higher number of it's cheaper to have a higher number of low power rating devices than a low number of high power rating devices. So it's always better to go for higher number of levels because the device ratings become smaller and smaller, although the device count becomes higher and higher. Now another thing is, if you see this as a problem that the device count is very high, then there is an option of using asymmetrical CHPs. So let's discuss briefly about asymmetrical CHPs. Suppose I have a CHP, I have an H bridge, this is an H bridge with an input of VDC, and it is cascaded with another H bridge with an input of 2 times VDC, which means now the input DC sources are not just electrically isolated, but they are also of different values. Let's see how these will add up. ठीक है, इस इन्वर्टर का आउटपुट हो सकता है VDC 0 and -VDC, और इस इन्वर्टर का आउटपुट हो सकता है 2 VDC 0 and -2 VDC, right? Now all these can add up in which configurations? VDC and 2 VDC can add up to become 3 VDC, right? VDC and 0 and 2 VDC can add up to become 2 times VDC. 0 and 0 can add up to become 0, of course, and no, we are missing VDC. VDC and 0 can add up to become VDC. 0 and 0 become 0. Minus VDC and 0 become minus VDC. -2 VDC and 0 become -2 VDC. And finally, -2 VDC and -VDC become -3 VDC. यानी कि सिमेट्रिकल टोपोलॉजी में when both the DC voltages were of the same value, in that case 2 CHBs were giving you a 5 level output, which we just saw. But if you are using an asymmetrical configuration, depending upon the type of asymmetrical values that you have chosen, then from the same number of switches, that is 4 switches plus 4 switches, that is 8 switches per leg, and then 8 into 3, that is 24 switches per whole converter. पहले आप सिमेट्रिकल कॉन्फ़िगरेशन में 24 स्विचेस से सिर्फ 5 लेवल आउटपुट जनरेट कर पा रहे थे, लेकिन इफ़ यू यूज़ एन एसिमेट्रिकल CHP, then these 24 switches will give you 1, 2, 3, 4, 5, 6, 7, a 7 level output, right? So a much better approximation of a sine wave if you use asymmetrical CHPs. However, everything comes with a drawback. Here the devices will be rated to a higher voltage, and the modularity of the converter is kind of lost, because these switches have to be rated at 2 VDC and these switches have to be rated only at VDC. So you're losing the modularity. It's not identical anymore. तो वो जैसे replicate करना आसान होता है modular converters को. You can easily just go on replicating them and adding CHBs. In asymmetrical converters, CHBs, you get the benefit that less number of switches and higher number of levels are possible. However, each H bridge is different because they are subjected to different voltages. Their ratings are different. So this was about Cascaded H bridge inverters, both symmetrical and asymmetrical topologies. I'm sure you have already studied in PWM techniques the level shifted and phase shifted PWM techniques for doing the modulation of these converters. Our basic goal is to move to space vector modulation of multi-level converters, and this is just to introduce you to multi-level converters. Now let's move to the second type of multi-level converters, that is the neutral point clamped converter, or you also call it the NPC converter or the diode clamped converter, right? The neutral point clamped converter, NPC. It's a multi-level converter topology. Suppose I have an input voltage, say 2 times VDC, and I split it using capacitors. So basically, unlike CHB, I don't have individual sources. I have just one source and I split it with the help of capacitors without any electrical isolation. It's the same source that is splitting through capacitors, right? So there are 2 capacitors and then there are 4 switches. Each of these has an anti-parallel diode, of course. And by diode clamping, neutral point clamped, this is the neutral point which is clamped to the in between the switches through diodes. So I have 2 diodes that clamp the middle point of the converter, or this neutral point, to potentials within the leg, right? And this is phase A of the converter. Similarly, I have phase B, which is exactly same as this leg, and even its diodes are clamped to the same neutral. Similarly, I have phase 3, the same 4 set of switches, 2 diodes clamping them, and the middle point of the 2 diodes coming back to the same neutral point. So I've just drawn one leg, because I don't have neither time nor space to, make the whole converter. But this is one leg of a neutral point converter. Now let's see how many levels of voltages it has. Let's see the pole voltage VAN. Suppose, let's call them S1, S2, S3 and S4. Suppose S1 and S2 are both on. S1, S2, S3 and S4 are both on. S1 and S2 are both on, and suppose S3 and S4 are both off. In that case, the output of my converter VAN is simply, this is VDC, because this was 2 VDC, it got split into VDC and VDC, right? So this N point is here, and from here the voltage that is appearing, S1 and S2 are both conducting, so from here the voltage that is appearing at A with respect to N is simply this VDC. So the output voltage VAN is VDC. Another configuration that we have is S1 is off, S2 is on, S3 is also on, and S4 is off, which means that the neutral point is directly connected through this diode and S2 to point A if the current in phase A is positive. So if current in phase A is positive, then this particular switching state means that current will flow like this, the diode will be forward bias, S2 is on, and N point is directly connected to A point, it's shorted, so VAN is 0. Or if the current is negative, then in that case S3 will be on, because S3 has been given a pulse. S3 will be on and the other diode will conduct, and it will bring the A point again at the end point. So VAN is 0. In this particular switching configuration, the output voltage VAN is 0 whether you have positive current or whether you have negative current. And finally, the last switching state in this converter is when S1 and S2 are both off and S3 and S4 are both on. So if you observe, you have the end point here. You are just going through the capacitor. These two are on and this point reaches here. So VAN is simply minus VDC, which tells you that the output pole voltage, if you may call it the pole voltage, is a 3-level waveform: VDC, 0 and minus VDC. So if you have n levels, you need n minus 1 capacitors, right? And you need जितने capacitors हैं उसके twice आपके switches हैं, right? So you need 2n minus 1 switches, 2n minus 1 switches, right? And what about the clamping diodes 1 and 2? There you require only 2 clamping diodes. You basically require clamping diodes जितने भी आपके switches हैं, that is ये pair of switches n-1 कह सकते हो, and then this is n-1, total is 2n-1, right? यहाँ पे अगर n-1 switches हैं तो इनके लिए n-1 डायोड है, क्योंकि इनके बीच के इंटरकनेक्शन में आपको डायोड लगाना है. सो दिस इज n-2 डायोड चाहिए टॉप स्विचेस के लिए, और बॉटम के लिए भी डायोड चाहिए ऑपोजिट डायरेक्शन में. सो 2 times n-2 clamping diodes. That means if you need an n-level output, you need n-1 number of capacitors to split your input single source of DC, split through capacitors, n-1 capacitors, and then you need 2 times n-1 switches, and then you need 2 times n-2 clamping diodes. So of course you can generate more switches, use more switches to generate higher level of output, say 7 level. This is simply a 3-level converter, 3-level NPC. You can generate a 5-level, 7-level or much higher levels of output. Now let's see the switching states in this converter. We have 3 switching states. This is one switching state, this is another switching state, and this is another switching state for one leg. So 3 switching states for A leg, into 3 switching states for B leg, into 3 switching states for C leg, which means that there are 27 switching states. Even in CHB, you saw that there are a large number of switching states. That's the beauty of multi-level converters, that you have a very high number of switching states. And when you have high number of switching states, you have higher degree of freedom. You have higher possibility of controlling things. So it's the same with neutral point converter, or neutral point clamp converter also, that to get a 3-level output, you have 27 possible switching states. And we will, in the next lecture, we will do the space vector diagram with those 27 switching states. So जहाँ आपके पास एक 2-level VSI में there are only 8 states, 6 active vectors and then 2 zero vectors. Total 8 switching states से आपकी space vector diagram बनती है. 6 से hexagon और उसके origin पे आपके 2 zero vectors होते हैं. But over here you have 27 switching states. So obviously जो आपका hexagon बनता है उसके अंदर भी आपको बहुत सारे points मिलते हैं. Again, those points show you a better approximation is possible using a multi-level converter. We will do that in more detail in the next lecture. For now, I think this is enough. So if you have any doubts or queries, please feel free to ask me. This was just like a revision lecture of multi-level converters. I did not even intend to teach you multi-level converters, because you have been taught multi-level converters in depth in your course on PWM techniques during your offline lectures. But I felt it was my duty to recapitulate a bit and to teach it from the perspective of switching states, so we can move on to a space vector analysis. That's all for today. Thank you very much. Bye bye.